All right. Hello, everyone. First thing I want to point out, as promised, the solutions are posted. So if you go to the Test 1 review, it's in the Test 1 folder. So if you go to the Files tab, you go to Test 1 review, because that's our Test 1 folder. If you go in there, it says Test 1 lecture, Fall 25. Boom, there's all the answers. The free response is also worked out. So great. What I want to point out are the two questions that the vast majority of people miss. This is the reason that there was any curve whatsoever. I don't do a curve to get the grade higher. The only reason I do a curve is if the data shows I have not prepared you well for some specific topics. Now, what's that data? It's your all's test. The two questions, not ones I expect. I can never really expect which ones. I might have guesses. They were both Gauss's law. Gauss's law was the thing we definitely had some difficulty with. One of them was kind of Gauss's law. You didn't even have to do Gauss's law. It's just whether you knew the answer, like the equation. So let me point out what both those questions are. The first one was, I can't zoom in. Thank you for mentioning that. Boom, boom, boom. The first one was, what is the electric field above an infinitely charged plane is E naught? What is the electric field running twice as far away? The answer is it's exactly the same. Why? So let me, let's see. Here, I'll just add them to this PowerPoint somewhere random. They'll get chucked into DC circuits up at the top. So I'm just going to copy and paste both of these questions. PDFs you can mostly copy. So great. What is the electric field some distance away? So basically, this was the one equation I told you all for Gauss's law that you might want to have written down in your formula sheet. The infinite plane. You could derive it if you wanted to. Anytime I ask you a question like this, you should write down the irrelevant equation. What is the electric field due to an infinite plane? It is sigma over 2 epsilon naught. This is the one we use for a capacitor. This is the one I said it a few times. Again, clearly something went off because maybe something didn't get mentioned. I don't know. I think people jump to Coulomb's law because almost everyone a lot of people put it changed by 1/4. That's to use Coulomb's law. That's a different electric field. That's to do a single charge. So what happens if I double the distance? Distance shows up absolutely nowhere in this formula. So what happens if I double the distance away? Nothing. That is a viable option. It's one of those, sometimes things change and nothing changes. And so how do you make sure you catch these kind of problems? You write down the relevant equation. And you actually look at the equation and be careful of that. That's how you're careful on a test. If you try to do it in your head, that's where you might accidentally have in your head been like, E equals KQ over R squared. If you write down that formula, you see this Q. If you think about what does Q represent, that's a point charge. That does not apply to this situation. Different electric fields for different geometries. So boom, that's one of them. That was one of the problems. The second problem did involve some math. So this one did involve you actually doing Coulomb's law. It was the one, a cylindrical wire with a charge distribution of 5 microcoulombs has a radius of 0.5. What is the electric field some distance 0.6 centimeters from the center? So this one you actually did have to do Gauss's law. Now, it was like one of the easiest, and I say one of the easiest cases of Gauss's law. Let me show you what I mean. So it's you draw the picture. So you draw your wire. And then we pick our point. And then you draw your Gaussian surface. So this is something really important for Gauss's law, is drawing the picture. Now, to find the electric field at this dot, we then do Gauss's law, integral of E dot dA equals Q enclosed over epsilon naught. What's my area here? It's the area 2 pi r times L. That's the area of the sides of the sphere. What's my Q enclosed? That's going to be my lambda times L. Because in this case, my units are a linear charge density over epsilon naught. We then solve for E. and you get lambda times L over 2 pi RL over epsilon naught. The L's cancel. We don't even care about the radius of this object because we're outside it. We have all the charge. You plug in the numbers, you get the answer. When I said this is one of the easier cases, this is one of those where you either have all the charge. In this case, we have like all the charge. The more complex cases are when we have some of the charge. And there was one of the free responses, and this one also from the tests I've seen, I've been very pleased. So if you recognized, so again, for these problems, if you just wrote that this equation that I'm going to solve the electric field, that gets you basically 4 to 5 points. What gets you the rest of it? Did you set your bounds correctly? In my case, actually, sorry, I need to update the solution. The solution previously had this, so I'm going to actually upload the correct solution. These bounds should be 0 to negative L, so I do need to update those. I've been grading them with 0 to negative L. So anyway, I'm just noticing I had a previous version and I fixed things, whatever. I'm going to fix the solution here, but 0 to negative L. Did you do the correct? If you're doing x component, did you put the cosine? Did you put the sine? Did you draw the picture? That's where you're getting the extra points.
How come the density is like a comma? Is that because of the two different versions of the test?
Yeah, there's different, so if you can see down here, you got the different versions. There's all the different versions on there. X component, Y component, different charge distributions. All right, this one, a lot of people struggle with the picture. And the key here was the last sentence. Both points are above the horizontal wire. So when you draw your picture, you should draw both points above the horizontal wire. I see a lot of people putting them on it. This is the one, the Gauss's law. And a lot of people recognize that for this insulating sphere, I needed to do a ratio of the charges. What was the mistake I saw is people didn't realize I just need to add the charge inside. So find that it's basically two charges. One, you have some of it, and the other you have all of it. So how much charge enclosed? Add them together. It's two objects. So what's the charge in my insulating sphere I have? You do the ratio. What's the charge of this little object in the middle? It's whatever it says it is. Just add those together. That was all you had to do to add them together. It was all in variable form. Then the rest is kind of all here. This one was pretty straightforward. Again, they're all here to look through, but Gauss's law is definitely the challenge. And I can guarantee you, on the final, I'm going to ask you a question about what happens to the electric field due to an infinite plane if I go somewhere else.
Can you give us extra credit if you don't do that? If you remember today?
If you remember, extra credit of what?
If you're going to give us that question, what if you don't give us that question? Do we get something?
Oh, gosh, no, you're going to get that question. That's always my rule. If there's a question the vast majority of people are missing, I didn't prepare you well enough for it, so great. I have now notified you of what the thing is and what you need to make sure you're practicing, the areas that we kind of missed. There might have been other areas you missed coming this coming week. If you want to come to my office hours, I can show you your test, your specific Scantron. I do not have the free responses, so if you come this next week and you want to see your free response, I don't have it. It's still being graded. I only have the multiple choice for you to review at this time. After this next week, I should have the free responses. All right. So great, there's that. Please look through those. It's worthwhile because the final is cumulative. Someone asked a really good question in my office hours. They said, what's the hardest test? I said, test 1 and the final. They're kind of tough. Test 1 is the hardest because it's new. You haven't seen a test in my class before. You don't know what to expect entirely. As much as I might say things, that's the reality. The final is tricky because it's cumulative. So, depending on your perspective, one might be easier than the other. Test 2 tends to be easier, not because the content is easier, but because you have a better expectation of, it's more expected of you, and it's not the final, it's not cumulative. All right, so last class, getting back to DC circuits. I taught you all 2 rules. The junction rule. I taught you that current adds together. What goes in must go out. And I also taught you that the voltages sum to equal 0 when we make this loop. So we're going to be practicing that today. Our 3 goals today is to finish up these 2 rules. We're going to do a problem with that, do resistors in series and parallel, and do RC circuits. And then we'll actually be done with circuits until in the future week we'll get to AC circuits. But next week we're going to get to magnetic fields. So we'll be kind of done with circuits after this. All right, so we did this problem. And this was a practice with doing this loop rule. The key to the loop rule is you pick a direction for current. You pick a direction to walk around this circuit. When I say walk, like obviously we're not physically, it is very helpful to imagine you're physically walking along this thing, physically moving through this circuit. We're going to apply that and you're going to see what I mean. So in this circuit, there's a lot of pictures here. I'm going to go ahead and erase some of these just to make it a little easier for us to understand. So in this problem, I said, this is the last one we did, I said, what's the equation for the total voltage drop? First, we define a direction of current. It's defined down here for you all. And because it's defined down here to the left, that means we can know the direction of current everywhere in the circuit. Remember, current goes downhill. Current, quote unquote, flows downhill. That's a very helpful thing to keep in your mind because voltage is what we're talking about. Voltage is like up and down. Current flows downhill. That's a really helpful thing. So, great. We got our currents. All I'm doing here, so yeah, there's going to be a bunch of rules you'll see in a second, but I'm going to say them now and then they'll be explicitly written in another slide. Next, we pick a direction to start walking. We make this loop. So in this problem, the loop is given. And in a lot of the problems, I'm going to tell you the direction, but it doesn't matter. We're going to go clockwise. So we pick some spot. Let's just say we're going to start at spot A. We pick some spot and we're going to start walking through this circuit. We're going to start physically moving through the circuit. So we start at point A, we're going along the wire, nothing happens, nothing happens, nothing happens. I then hit the battery. And my question is, when I hit this battery, the voltage is going to change. So the question is, do I go uphill or downhill? If I start on the negative terminal and I'm moving to the positive terminal, I'm going uphill. Hopefully we're all cool with like negative to positive. We're going to go uphill. So I'm going to write 12. Positive 12. I went up by 12 because I'm going up the battery. Great. I'm walking. I hit a resistor. Is my voltage going to go up or down? We have to look at the current. Current flows downhill. So the direction we're going, if we're going in the direction of current, we're going downhill when we hit this resistor. How much do we go down? I times R1. V equals IR. Why did I go downhill? Because it's the direction of current. All right, great. I hit this resistor. I keep walking. Nothing happens until I hit a resistor or a battery. That's the key here. Great, I'm walking. I hit another one. I see the direction of current. The current, again, is going the direction I'm moving. I'm still going, quote unquote, downhill. So I subtract IR2, and then I'm walking, hit the other resistor. Again, going in the direction current's flowing, going downhill. And eventually I end back where I started, so I'm done. All that equals 0. This is the process. This is the voltage rule. This is the loop rule. You walk through your circuit, you walk through a loop, and you build this equation. Electrical engineers are going to have to do this a lot.
This might be a dumb question, but like, you say start at any spot. Does it have to be one of those dots?
No, that is a great question. The question was, does it matter where I start? Do I need to start at one of the corners, one of these dots? No. Pick anywhere. If you pick somewhere over here, you would just rearrange this. And because it's addition and subtraction, the order doesn't matter. That's a very good question. If I had instead picked a different spot, say I started over here, it would just rearrange the terms. But 2 plus 3 is the same as 3 plus 2. The order of these doesn't matter.
If you have a parallel circuit, will the equation change based on the path?
Yeah, that's a great question as well. If I have a parallel circuit, will the equation change based on your path? Yes. And what I am building us towards is doing this problem where we're going to build 3 loops. So I'm going to kind of go through that one a little bit quickly. So that's why I'm going slowly right now through a simple case, and then we'll do it 3 times for this one. All right, let's see if this made sense. Same circuit, but now go the other way in the loop. Instead of going, the current is still in the same direction, but now walk the other direction and build the equation. If I go counterclockwise, pick a dot, walk through your circuit, ask yourself, every time you hit a resistor, am I going uphill or downhill? Every time I hit a battery, am I going uphill or downhill? That's the mindset. And imagine you're physically moving through this circuit. Trace it if you have to. It's a very useful exercise. Kirchhoff's laws is one of those notoriously things that just confuses a lot of people. But if this is the process, if you can understand this walking and this uphill, downhill thing, it's not bad. You all walked before. Do you know which way water flows? Use that. All right, so there's a bunch of answers here. They vary by positive and negative signs. So it's really determining, can you determine whether or not you're going uphill or downhill? And it's useful to go with currents and each resistance. It's useful to go with currents and each resistance. No, I'm walking through this thing. Yeah, the current is still defined the direction we said. We're just now walking. Yeah. And the reason that matters is before, if we walked in the direction of current, we walk downhill. If we walk opposite the direction of current, we're going up. That's the important thing here. All right, give y'all about 20 more seconds on this. All right, we'll close this one out in 5, 4, 3, 2, 1. All right, so we're going to do the same practice. First, I'm going to draw the currents through every resistor. That's going to be very useful for us. How do I know the directions of the current? I have one little picture down here that says the current goes to the left on the bottom. And so it's a one-way road. You can figure out the directions everywhere else. Boom. So there's my currents. If you don't draw those, that's going to make your life harder. We then pick a random dot. I don't care where. I'm going to pick this dot here to the right of R1. Doesn't matter where. I start walking counterclockwise. I hit my first resistor. I'm going opposite the direction of current. So if current flows downhill, and I'm walking opposite the direction of that, I'm going to be walking uphill. If current flows to the right, then that's going downhill. I'm going the opposite direction, that's uphill. So it's going to be a positive I times R1. Because I'm going opposite the direction of current. Great. Then I keep walking. I hit the battery. The positive terminal is the high. The negative is the low. So if I'm going from the positive to the negative, I am going downhill. Positive is high, negative is low. I don't care the direction of current for a battery. How do you determine the voltage battery, whether it's positive or negative? You just look at the battery and say which side's high, which side's low. Again, physically move through it. Then walking. I hit this resistor. I'm going opposite the direction of current. So yet again, I'm going uphill. And I know these were mislabeled, but you get the idea. Walking. Hit the last resistor. Again, opposite the direction of current. Therefore, I'm going uphill. And there's my equation. Now you can see none of these look like that exactly, but if you rearrange it, you get the last answer. They're the exact same thing. Now, something I want to now also point out to you all is answer C and answer D are mathematically the exact same equation. Answer C and answer D are exactly the same. How do I make it from one to the other? If I just multiply both sides by -1, it turns into the other equation. Why am I telling you this? The direction of your loop doesn't matter. I told you all the direction of the loop, but if you happen to pick the other direction, you get the same answer mathematically. So these corrections I'm picking to walk don't actually matter as long as you're consistent. As long as you're actually moving in the direction you say you are. Again, this is very important. The reason I'm spending the time on this is electrical engineers and physics majors need to know this stuff. Mechanical engineers, maybe not so much, but every circuit software is doing this math. Every circuit software is doing the two rules, junction rule and this. And even mechanical engineers, you all need to know how to work with electricity as well. Aerospace engineers, you need to work with electricity as well. Why? Everything runs on electricity. Like, you might not interact with... You're going to interact with electricity in your lifetime. You should probably know how it works. And this is like the basic rules for complex circuits. All right, so it is relevant. Even if it's not, this just process of doing complex things trains your brain. So here it is explicitly. Here's the two laws together. Current in equals current out. Sum of voltages equals 0. Here's the process. We've been doing this the last two slides. Draw the directions of current. Draw a loop. Draw a path you're going to walk for the loop rule. Build the voltage equation by walking that path. Build the junction equation, the current equation. That's the junction equation. I'm going to relabel this. The junction equation, which is the current in, current out, wherever there's a junction. Use the system of equations to then solve. That last one you're going to largely be spared. The system of equations is very common in these Kirchhoff's law problems to have like 3 or 4 equations with 3 or 4 unknowns. And any of you that are in statics class knows the joy of solving a system of equations. And that it takes longer than I have the time to test you on. So we're not actually going to be solving these systems of equations in this class very often because it's just algebra. And I don't want to waste a bunch of time on a test doing algebra. But you need to be able to build these equations. That's what I'm going to test you on. On a test, I'll give you a picture and say, build the junction rule for this through this. Or build the loop rule for this. So, here's an example of one of those questions. Here's a circuit. It is a complex circuit. Why is it complex? It's got multiple batteries and multiple resistors. You have to use these rules if you have multiple batteries. Is basically the rule of multiple voltage sources. So it says build the 3 loop equations and the 1 junction equation for the following circuit. Now, normally in these problems, the problem ends there. It doesn't tell you anything else. Because I want us to all get the same form of the equation, I tell you the directions of current. But normally you would actually define it yourself. But so we all get the same looking equations. I make some things explicit. But this is just random. In fact, one of these currents is in the wrong direction. Doesn't matter. You do the math, it fixes itself. We already went over that. All right, so make I1 pass down through this resistor, through the 50 ohm. Make I2 pass right through the middle resistor, or through middle battery. Make I3 pass right through the 100 ohm. Are these the correct directions of current? Some yes, some no. Does it matter? No. When you do the math, if one of these is wrong, and I'll tell you I1 is technically wrong, the math would actually get you a negative. And it will get you a negative when you solve for it in this problem. What does that mean? It's not going down there, it's going up. And that's fine. It fixes itself. But just to let you all know, in other classes, they're not going to tell you the directions of current. You just pick them. Make a guess. If you're wrong, it doesn't matter. Same with the loops. I tell you the direction of the loops. In future classes, they're not going to tell you the direction of loops. You just pick one. It's fine. All right. First step, I'm going to do the junction rule because that's the easiest. So I'm going to pick a junction. There's a junction. And all I need to do is draw the currents going in and out. So 2 of them are already kind of next to it, so that's kind of nice. I1 points into it, I2 points away from it. What about I3? Just move I3 closer to it, and it's easier to see. Great. So the junction rule here, really easy. It's I1 equals I2 plus I3. What goes in must come out. Boom, there's one equation. Very easy. But what if you're like, oh man, I picked the other junction instead. I picked this junction on this side. All right, let's do that one. I2 is pointed into it. That's pretty easy to see. I3 also points into it. I1, so I1 on this side is going down, which means it's doing this whole loopy motion. So which way is I1 on this side? I1 is up. It's good exercise to practice drawing these. So what does that mean for me? That means that I2 plus I3 equals I1. It's the same equation because in this circuit it's simple enough that it works out that way. It doesn't always work out like that, but in this case it does. Yeah.
Why is I1 doing the loop thing? Like
Oh, yeah, and the problem, it says I1 is going down through the 50 ohm resistor.
So how's that get to the right?
Yeah, that's a good question. Just to clarify that, remember each of these branches is a one-way road. So it's a one-way road. So if I'm going down on the left side, then I'm going left on the upside, then I'm going right up on the side. Yeah, it's good to it's a one-way road. Each branch is a one-way road. All right, these are good questions. All right, next, the loops. For you to do the loops, you got to even figure out what loops there are. Rule of thumb with the loops, you shouldn't go back on yourself. It's like one of those, have you ever seen those puzzles where they draw a bunch of triangles and then they say, how many triangles are there? It's kind of like that. How many loops can I draw in this picture? The answer is 3. 3 loops that don't go back on themselves. 3 ways I can move around this circuit where I don't backtrack. 3 paths I can take. So the first loop is through this top little thing up there. I'm going to color code these differently, and we're going to use that to build the equations. The second loop is going to be this one down here. All of these are counterclockwise. Why? Because we just chose in the problem to make it that. Does it matter if you picked clockwise? No. The last loop is the entire thing. There's the last loop. 3 big loops. Each different than the last. On a test, what would I ask you? I would ask you for the loop. So one of the quiz questions on this upcoming quiz, I'll tell you, draw the loop through these 3 elements, or these 4 elements. So like, for example, I would say, give me the loop equation through the 5 voltage battery, the 50 ohm resistor, and the 12 volt battery. Or give me the loop equation through the 12 volt battery and the 100 ohm resistor. Or give me the loop equation through the 5 volt battery, 50 ohm resistor, and 100 ohm resistor. Those are the 3 paths that we have here. So now I'm just going to quickly write down what each of these are. Again, we pick a spot and we physically move through the circuit. I will do this for one of them, and then the rest I'm just going to kind of write them a bit quicker. So this loop up here, we're going to the battery. We hit the battery. We go from this, and this is something I also want to point out. This is a notation I might not have taught you. This is a battery. The small end is negative and the big end is positive. Hopefully that's kind of what you want it to be, and that's what people have made it. Big end of a battery is positive, small end is negative. This is very common notation for circuits. Okay, so we hit this battery, and I'm going to zoom in a bunch so we can see what's going on here. So we hit this battery, and we're going across the battery from the negative to the positive, so that's going to be plus 5 volts, because I went from the low to the high. Then I keep walking. I hit this next resistor. This resistor, I'm moving in the direction of current. I'm going downhill. If I'm going downhill, then I put I1 times 50, I times R. Then I keep going, keep making my loop. I hit the 12 volt battery, high end to low end. That means I'm going to go down because it's positive on this end, negative on this end. And then I keep walking and I end where I started and boom, done. That's the loop rule for that. All right, again, now the next ones I'm just going to kind of write quickly. The green one, we pick some spot. We go counterclockwise. We hit the battery. That's positive 12. Walking. We hit the bottom one. That's going to be minus because we're going in the direction of current. And that's all there is in the bottom circuit, the bottom loop. We then do the last loop, the big old loop. Pick any spot on that loop. Now, what's important on this loop, do not start in the middle. That loop does not include the middle path. This loop is a loop. It sounds stupid. Do not make this a figure 8. Do not make your loop this crazy 8 shape. That's not a loop. That's a twisted, it's not a loop. Hopefully we're cool with that. The loop is just this big old loop. All right. Now, these loops can take angles and things like that, but what's important is you never cross yourself. You never cross the loop. That'd be weird. All right, so we pick some spot. Sure, let's pick here. We're going through this resistor, so that's going to be negative I1 times 50 because we're going in the direction of current, downhill. We hit the bottom one. That's also going to be I3 times 100. And then we head on up here and we hit the battery, and that's plus 5 equals 0. And that's that loop. Now, unfortunately, in this circuit, I say unfortunately, all the IRs were negative. That is not always the case. Don't get in the bad habit of always making your I times R is negative. Sometimes it's positive, sometimes it's negative. How do you figure out? Walk your loop.
Why spelled negative in the first one?
Yeah, it's all based on the direction of the loop. That's a good question. So in the first equation, when we made our loop, we were traveling counterclockwise, and we went from the positive terminal to the negative. So when we made this purple loop, we're going clockwise. Here, I'll trace it with my finger. When we're going like this, we hit the positive terminal, and we go to the negative terminal. So we went downhill. When we made this green loop down here, when we're walking this loop, we went from the negative to the positive. So it's all about when you make this loop, which way are you traveling when you travel through that thing. This top loop, I'm traveling this way. When I go through this battery, I'm going to the right. When I do this bottom loop, I'm traveling to the left here. Yep.
So then if you want to find the current, you just solve for I1.
Yes, exactly. If you want to solve for the current, which this problem does ask us to do, this problem is actually pretty easy to solve. This one you don't need a system of equations to solve. I purposely made this one simple so you didn't have to do a system of equations. We built the system of equations, but if you notice my first equation only has one unknown, my second equation only has one unknown, my third equation has two unknowns. If I go to the problem set, there's another example of this where that is not the case. Where when you build the loops, you get two unknowns in one equation. And yeah, problem set 2, oh yeah, thank you. Wrong one. Problem set 2 is updated for this week and next week. Again, it's an ongoing process where I'm updating these things. They technically have problems in them from last time I taught it, but they're not. Yeah, this week and next week are updated. At least they'll update once I upload the file. All right, so this one. If you look at these equations, these are loop equations you're going to build. This first equation has two unknowns. Second equation has two unknowns. Third equation has two unknowns, meaning system of equations. Solve for one, plug it in, have a great time. That is something that electrical engineer, I'm not going to ask you to do that on a test, but electrical engineers should be able to do that. Mechanical engineers, you get to do statics with systems of equations. Electrical engineers, I don't know what class, you'll have to suffer through this.
So, like, on these kinds of problems, how do we know, like, how can we, like, I guess, check and see if, like, we got negative?
Yeah, so in these problems I tell you the direction, but if you're actually solving this and like solving it out, you just pick directions, and as long as you're doing it correctly, it works out. If your current's wrong, it'll spit out as a negative. It fixes itself. All right, so great. That one's done. On to new and exciting things. This is going to be a pretty quick derivation. We're going to talk about series and parallel. These are the simpler ones. If you only have resistors in a circuit, not always, but pretty often, you can just combine them into one resistor, just like we did with the one capacitor. Same technique, different equations. Remember, in series, current is constant. How do we know that? It was the first clicker question I asked you at the beginning of this PowerPoint. The one with the whole water wheels. You all were pretty cool with that. Current's constant in series. In parallel, what's constant? Voltage. The current is not the same. Cool. We're going to use that. So, there you go. Previously, you all built this equation. By previously, it's the questions that we just did. Great. Why is this useful for us? It's going to help us with the derivation. These are in series, so we can use the equation you all built. If they all have the same current, pull it out. Behold, I have pulled out the current because it's the same for every single one. What am I left with? Addition. So how do you combine resistors in series? Just add them together. It's an easy derivation from the equation that you all derived this equation. That was the clicker questions that we were just working on. If they all have the same current, factor it out. What am I left with? Resistors that I can add together. I.e., I can turn them into one resistor. So this is, how do you turn, remember we did the capacitors? How do you buy a bunch of capacitors in series? So there's going to be a nice little summary slide. Resistors, you can turn it into one resistor. In series, you add resistors together. For capacitors, this was true in parallel. They have opposite rules. We're going to have a nice summary slide showing all the rules in a second. So great, that's series. That's a derivation. Series, add them together. Why? Loop rule. How are we going to do the parallel? Junction rule. All right. Great. There's a nice summary slide. In series, when you add them together, you always get a bigger resistor. There is no such thing as a negative resistance. There is no resistors with a negative resistance. They just don't exist. Because what would a negative resistor mean? It would mean when I apply a voltage, current flows the opposite direction that we think it should, which is not. We have not discovered a device that does that yet. The best we can get to is zero resistance, and that's a superconductor. A superconductor is a material whose resistance is zero. And you get some crazy things with that if you all kind of think about this equation, V equals IR. If you apply a voltage and the resistance is zero, what does that make your current? It doesn't become infinitely large. I don't actually have that resolved in my head. It just doesn't obey this equation so much anymore. But what you can do, which would be really cool on a superconductor, is you can put a current on it, and that current will last like forever, as long as you don't use that energy for something else. That current will just kind of keep cycling around forever and ever 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 and ever.
Do you have an example of that?
MRIs. They use the energy from. We're going to learn that currents make magnetic fields, and you steal the energy from that and you use it for things. But yeah. So anyhow, great. Resistors in series. Easy. All right. Build the junction rule. We already built the loop rule to derive series. Build the junction rule so we can derive the parallel. I have some parallel here. Why are they in parallel? Not because they're physically parallel, but because they have the same voltage on each side. Don't forget that. They have the same voltage on each side. So I have some current going in, and then each branch gets a current. R1 gets I1, R2 gets I2, R3 gets I3, R4 gets I4. In equals I out. Do it to it. All right, give y'all 30 more seconds. Oh, and there's two right answers.
Okay.
There's a reason why there's two right answers. I'm going to tell you why. All right, we'll close this out in 5, 4, 3, 2, 1. All right, so there's two right answers. We're going to first do it the way I showed you all, and then I'm going to talk about why there's another answer that's right. I mean, mathematically they're the same. That's the answer, simply. In equals I out. So we look at our junction here. Which currents go in? I net. Which ones go out? Everything else. Everything else is pointed away from that junction. So you get I1 plus I2 plus I3 plus I4. So great, that's the answer. So this is going to be answer B. What goes in equals what goes out. This is one way of writing it. Now, the question was, should they be negative? And that actually does prime us for another way to solve this. So what I'm going to navigate to is Wikipedia. And you're like, why am I going to Wikipedia? All will be revealed once I can make a new tab. Oh, real quick, I just want to point out, I keep mentioning using AI stuff. I'm using AI stuff. What am I using it for? I'm building your all's PowerPoint for next week on magnetic forces. And something I wanted to look up was the history on where this came from. I told you everything comes from observation. So what did I do? I asked ChatGPT, I'm teaching about magnetic forces at University of Physics 2. Can you provide me some history on how this was discovered? It then provided me some history, but because I didn't just want to trust it as is, I had a follow-up. Can you provide sources for these so that I can know that the information is accurate? And boom, then it provided a bunch of sources. Wikipedia is very good, so generally when I see that, that's a good sign. And then I asked some more follow-ups. These are the things you can do with it. You can ask it a question. If you're unsure, ask it for sources, ask it for examples, ask it for links to YouTube videos where they're solving problems like it. Use that thing. This basically synthesizes the internet. That's what it was trained on. And it now has the ability, and again, you don't need to use ChatGPT. You can use any of them, Gemini. I don't want to sound like a shill for ChatGPT. It's just the most popular one. But Gemini, Copilot, pick whichever one you have the paid version of, and it'll probably do better than the free versions of the other. That is a reality. All right, can I move this box out of the way? No, I'm going to have to do it All right, so Wikipedia, junction rule. Why am I looking this up? On Wikipedia, the junction rule is listed as this. Sum of currents equals 0. Why do they write it this way? They say currents going in. I guess it's arbitrary. In this case, let's say that currents going in are positive and currents going out are negative. It doesn't actually matter which way you define it. What's important here is they just put it all on one side. So if we look at this equation here, if I instead decide to use that equation and I just say sum of currents equals 0, and I decide in is positive and out is negative, what's going in? I net. What's going out? I1, I2, I3, I4. These are all negative. Minus I4 equals 0. Oh my gosh, it's the same exact equation. Just move the stuff to the other side and you get the same one. Sometimes these equations are written in two different ways. Mathematically, they're the same thing, though. That's all that matters. In the English language, we have synonyms. I could say something is excellent, or I could say something's really good. It basically means the same thing. Math, same thing is true. Math is a language. Don't forget that. And we have synonyms, as long as you follow the right rules. All right, great. Why does this matter? All right, so we start there. We start with the equation you all just arrived. We replace I. Remember that V equals IR. Therefore, I equals V over R. I'll use, it doesn't really matter. Well, for the sake of notation, I'll put it as delta V. Anytime we say V, it's always delta V. Swap it in there. Everywhere there's an I, put a V over R, V over R, V over R, V over R. In parallel, what's the same? Voltage, so they all cancel out. What am I left with? In parallel, if you want to get the resistances, add the reciprocals, and then do 1 over that. So great, that's parallel. Here's a nice little summary slide on it. What's the point of this? 1 resistor is easier to work with than 4. It's easier to work with one thing than 7 or 10 or however many you might have. Note, this is something very important. When you combine in parallel, this is a very helpful rule to have in your head. When you combine in parallel, our net will always be smaller than the smallest resistor in that circuit. Always. The net resistor will always be smaller than any. If I pick one of these and it was 0.00001 ohms, my net resistance is going to be smaller than that value. Why? Mathematically, that's how it works. That's just how this math works. Conceptually, very easy to understand. Think of each of these like a road. What am I doing when I'm combining them into one resistor? I'm taking all the lanes and smashing them together. So I'm going to have less resistance if I smash a bunch of roads together. At the end of the day, what is resistance? It makes it harder for things to flow. Well, if I got a bunch of lanes and I smash them together, that's really easy to flow through that. This is a 2-lane highway, 3-lane highway, 5-lane, 7-lane. How many lanes do I have? Again, we're not actually physically adding them. This is a conceptual thing. We're making a big fat wire. Take all these wires and cram them together. And boom, you got a fat wire with low resistance. That's the idea. All right. Cool. Yeah, we'll do this one very quickly. I just need to get to RC. Oh, we're actually doing all right. We just got to get to RC circuits after this. What is R1 in the following circuit, given that the current through R1 is 1 amp? You could, I suppose, solve this with Kirchhoff's laws. Fun fact, if you use the loop rule and the junction rule, you'll end up just rederiving the series and parallel. So if you can combine your resistors, do that. If you can combine your resistors, do that. If not, junction rule and current rule. How do you know which one to use? Combine them if you can first, and then do the rules. The less resistors you deal with, the lot easier your life is.
Why is it like the names like let's go from R1 to R4 to R8?
Because that's a picture I stole. That's a good question. Yeah, it's just a picture I stole from online, and they labeled these like this. I don't really like this one being, whatever, it's fine. I'll leave them as is. It doesn't really matter. It's just labels. Generally, I do label these just like 1, 2, 3, 4, 5, 6, 7. But whatever, it is what I have. All right, so first step, we combine what we're allowed to. You can only combine things that are purely in series or purely in parallel. Spend 20 seconds thinking about which ones you can combine. Don't yell it out, just think about it. And I'm going to go ahead and move this over to the other side. Every time you solve this problem, you're going to draw the circuit every single time we combine things. That is key to doing these. Oh, look, see, there was a resistor value below there. That's not the right answer. You can see the tricks I used to make these problems. So. All right, if you realize that these two are in parallel, good job. Now, in this case, they physically look like they're parallel. Again, don't get in the bad habit of that. What's the actual reason? On this side, they have some voltage. On this side, they have the same voltage. They're in parallel. Make sure that's the habit you get into. It's like in physics 1. Don't get in the bad habit of cosine is always x and sine is always y. Just because it's often done that way doesn't mean it's always done that way. And this is the real rule. All right, whatever. These are in parallel. Awesome. So turn them into one resistor. R1 is still mystery. This one is now RA4 because it's A and 4 together. How do I find RA4? I'm going to do that up here because I don't want to do it down there. So it's 1 over, and I skipped a little step algebra-wise. This used to be 1 over. I just moved to the other side because I didn't want to write it a second time. 1 over 3 plus 1 over 6. 1 over 3 is 2, 6. That's 3, 6. So I'm actually going to write this out. So this is going to be 3 over 6. So this is 2 ohms. How do we check our work? 2 is smaller than the smallest resistor. 2 is smaller. What's the smallest one? 3. 2 is smaller than 3. Yay. If you got a number that was bigger than 3 or a number that was bigger than 6, you did it wrong. That's useful checks. Great. This is 2 ohms. Cool. Now, these are hopefully obviously in series. So now we're going to combine these into one resistor. What are we going to call that resistor? R1A4. What's the value of RA14? It is R1 plus RA4, which equals R1 plus 2. We don't know the value of R1. That's the entire point of this problem. Now, something we didn't, something to remember. Always keep this in mind. What am I even solving for? Always keep your target in mind. It's very easy when doing problems to forget what you're even doing. Have it written somewhere in your paper. I should have done this. R1 equals question mark. Just write that somewhere so that when you lose track of what you're even trying to find, it's written somewhere for you. It sounds stupid, but you will end up in this situation where you'll be doing so many things, your brain will get so caught up, you'll just forget, why am I even doing this? Have it written somewhere. All right. So now what? How do I figure this out? The beautiful thing of having one resistor is it gets the entire voltage of the battery. Why is that useful? Now I know that the voltage of 1A4 equals 9 volts. Why? Because it's the only thing connected to the battery. One side's 9, one side's 0. It's 9 volts. How is that useful? There is something in the problem we haven't written down yet. The current. And it says the current through R1 is 1 amp. How is that useful for us? We have to remember another rule. In series, current is constant. In series, current is constant. How is that useful? These are the questions that you kind of have to ask yourself. If the current through this one is 1 amp, the current through this one is also 1 amp. The current through this one is also 1 amp. Puzzle pieces start coming together. This is not a trivial problem. Like you have to understand what you're doing to solve this problem. You need to understand the concepts in the math to be able to do this problem. Great. How is that useful? I know voltage. I know current. If you ever know 2 out of the 3 things, you can find the other. V equals IR. Rearrange that. R equals V over I. How is that useful? I know V. I know I. What does that let me find? R1A4 equals voltage through 1A4 and the current through 1A4. That equals 9 over 1. What's my resistance? 9 ohms. And it's a very small step to find R1. R1 equals 7. 2 plus 1 equals 9. 7. But this problem is like, may or may not look deceptively simple at first. But you have to realize that the current's the same in series and you can do that step. Yeah. Yeah.
How did you, I guess, in the R84 calculation, how were you able to bring that big one up top?
Yeah, that's it. So just to remind you, it's a great point. How did I know that the 1 amp went here? Which big one?
When you solve it for R84, that one, like the giant numerator one, how'd you get that to?
He's asking how is it 1 over RA.
Oh, yeah. I'm going to actually go back to this slide and just write this out. R nets, if you just do the math here, is 1 over R1. If the thing you want is 1 over, algebraically you just do 1 over the other side. Yep, those are equivalent math statements. Yeah. Yep, that's a good question. I skipped that step, but that's the logic. Please, these are great questions. I always appreciate when people ask this because if anyone ever has a question like that, I can guarantee at least 10 to 20 to 30% of people do as well. I have been doing physics for so long that I take things for granted, and I may forget the things that are confusing. You all have forgotten how hard it was to learn to walk. My 1-year-old is very aware of the challenges of walking. The same is true of you. You are learning things for the first time, and when I've been doing it for a while, I'm only going to get worse at this as time goes on, as far as remembering what it's like. So please do ask questions to remind me what things I need to be more explicit about.
Were you in the other problem?
The power, that one's really easy. We can. Power. What's the power dissipated? PIV. P equals IV. So what's the power dissipated in the entire circuit? It's really easy. Take your 1 resistor, P equals IV. This is another beautiful thing about doing this. I don't have to work my way backwards and find the power in each element and add them up. Just get the net resistor, P equals IV. What's the power in this circuit? 9 watts. Done. One resistor is way easier to work with than 3.
Why do you need a resistor?
You do need a resistor to dissipate that power. Yeah. Good question. All right, great. Here's a summary comparing resistors in series and parallel. Why is this important for us to remind ourselves of? The opposite rules. And when we get to the final, test 2 will not have capacitors in series and parallel. Test 2 will not have capacitors in series and parallel. Test 2 will have resistors in series and parallel. The final will have both. So it's good to remember, that's why I'm reminding you all of this, they're opposite rules, and it's very easy to mix them up. On the formula sheet, I just put them. I don't tell you which one's which. I don't tell which one's series, which one's parallel. That's up to you to remember, or put it in a card. So this is a nice little summary of that, clearly showing they follow opposite rules. Clearly showing that in series, resistors add, and parallel capacitors add. In parallel, resistors are the reciprocal. In series, capacitors are the reciprocal. Why? Because we derived them, and that's how it works out. And there's not much more to say about that. Okay, we only have one more thing to cover. So the last thing is to teach you, what if I have resistors and capacitors in a circuit? The good news is you're going to be spared the worst of this. Like, this is just going to be, here's the equations. I will very briefly talk about the derivation for it. The reason I can't have you all derive this like a test or anything is it's a differential equation, which you might be intimidated by, but they're really not that bad. But you haven't learned how to do differential equations yet, and I'm not going to spend a bunch of time teaching it. So, all right. Yeah, what if you have both? What if you have a resistor and a capacitor? Now you'd be like, why would I ever have this? Every circuit has resistors and capacitors. I can guarantee you any circuit board you ever look at is going to have both. How do you know it has both? Everything is a resistor, so that's a given. Every single circuit has resistance to it. Resistance is just everything resists. If you ever look at let's just Google circuit boards. Just pull up a bunch of random pictures of circuit boards.
Wait, everything in life is a resistor?
Everything in life is a resistor if you try to pump current through it. Yeah. Okay, unfortunately these are blank. Whatever, let's see if we can find some. Great, here's a circuit board. All these cylinders are capacitors. Everywhere you see a cylinder, that's a capacitor. There is other types of capacitors. Potentially some of these things might be capacitors, but these cylinders are capacitors. So anytime you all look at a circuit board, I think, I don't know what those are. It's hard to say. Some of these can be, some of these little like packages can also be other things. Some of these could be inductors. We're going to learn about inductors eventually. But rule of thumb, if you see a cylinder, it's probably a capacitor. Every single circuit has capacitors on them. The entire circuit has resistance, so like they're just everywhere. They're all over the place. It's a little trickier to kind of see them on these circuit boards. So for example, this one labels resistor, capacitor, capacitor, resistor. They generally aren't labeled though like that. They take all shapes and forms. Anyway, all I'm trying to tell you all is that every circuit's got both. So you got to deal with them. Why? What's the purpose of an RC circuit? So here's the idea. Here's what's going to happen. What we're going to do is we're going to close this circuit. When we close this circuit, what's going to happen is the charge is going to start to flow and it's going to hit this capacitor. But here's the problem. It can't jump that gap. It can't jump that gap. So what's going to happen? As time goes on, and I showed you all a while back a simulation of this on FETs. As time goes on, more and more and more charge is going to build up on this, and the opposite type is going to build up on the other side. That won't happen forever. Hopefully that's not a big jump to say that obviously I can't charge a capacitor with an infinite amount of charge. A bucket can only hold so much water. Why do I say that? What's going to happen when it gets fully charged? I can't put more charge on it. If I can't put more charge on it, current stops flowing. So eventually, current stops flowing, and this takes a certain amount of time. It is very, very useful to have devices that stop working after a certain amount of time. What is that effectively? It's a clock. It is something that will run, the current will flow for a certain amount of time. Then, once it reaches that, what might you do? You then have some smart system in your circuit to then close. So again, we see that first case here, we charge it. We then close the other branch. We close this branch. What then happens? The charge, again, if we think of the current, will now flow the other direction. It will discharge. So you get charge, discharge, charge, discharge. You have an oscillating cycle of on, off, and actually the current flowing backwards and forwards. This has an immense number of applications to it. Some of them are timing. So for example, windshield wipers use RC circuits. What you're doing when you're turning the knob, you know how you have the variable thing where you can like make them flip-flop faster or flip-flop slower? You're changing the resistance value. It's a variable resistor that you're changing, assuming it is analog and not digital. Another case of a pacemaker, again, a timing. You want it to trigger ever so often. Timer. In other cases, in AC circuits, they limit your frequency. You can make a high-pass filter, meaning you let high frequencies through, a low-pass filter, you let low frequencies through. You don't need to know any of this, but there's uses.
Are we going to talk about diodes in this class?
No. That's a good question. We will not. Diodes are something that let current only flow one way. We're not going to talk about those, though LEDs do count as a diode, whatever that's worth. Yeah.
So if it's, you close it once it has enough charge and it keeps going in that loop, doesn't some of the charge also go to the left instead of up?
Yeah, so what's important here is only one of these is open at a time. So I connect this one, so current can only flow along this loop. And so it eventually charges completely and then stops. And that's what this circuit in the middle is.
And then when you close it the other way.
When I close it the other way, then the other one's open.
So there's some of the charge.
It can only make a loop. Current can only flow if there's a beginning and an end. You have to have an end point. Yeah.
So basically the switch is kind of like a crossing guard for using like.
Yeah. The switch is a crossing guard, and you can only go if the path is open. Yep. Just like when you don't have a battery, you always got to connect the two ends. You got to see a high and a low voltage, otherwise nothing will happen. Yep. And at the time of when this is fully charged, this has the same voltage everywhere on this wire. Nothing's going to happen. The second I then connect it, it sees another voltage and it goes to the charges go to that. All right. So great uses, important. Practice your Kirchhoff's laws. So here's a circuit. Now there's one thing I haven't taught you that you need for this, but hopefully it should be pretty straightforward. So in this problem, it says, what would be the loop rule for a circuit with one battery, one resistor, and one capacitor? Assume a current that goes, as shown in the picture, to the right through this. Use a clockwise loop. The only thing I need to remind you all of, I even tell you, C equals Q over V. Which end of the capacitor is the high voltage? The one with the positive charge. Which is the one with the low voltage? The negative charge. So which end is the high end? The positive side. Which end is the low end? The negative side. That's going to tell you whether you're going uphill or downhill when you walk around this circuit. So this is something you all can do. There's nothing crazy here. Try it. Build the loop rule. No differential equations yet.
No.
They're very subtly different. Yeah. It looks the same. That was purposeful. Yeah, but good thing you pointed that. Someone might have made that mistake as well. Yeah, so answer one says V minus IR minus Q over V. Next one is V plus IR plus Q over V. Next one is V minus IR minus Q over C. Yeah. And then V plus IR plus C. Yeah. Good. Again, I'm glad you mentioned it because you spared someone getting a wrong answer. Hint to you all, you're summing the voltages. You're summing the voltages of each element. All right, give you all 20, 25 more seconds. All right, in 5, 4, 3, 2, 1. All right. So remember, it is always helpful to know the direction of current where the resistor is. So we're just going to put that current next to that. That's the only resistor. Capacitors don't care about the direction of current. You'll see what I mean as we solve this. So we pick some spot in our circuit. Let's just pick down here, and we are going to go clockwise. Why? Because that's what I said in the problem, just to make sure we all got the same answer. You pick any spot you want. In fact, let's do this spot instead. Doesn't matter. You pick somewhere to start. We're going to start, sure, we'll start up here just to prove it doesn't matter. We're going to walk. We hit our first resistor. We're going in the direction of current, so we're going to go downhill. So I'm actually going to write this like this, the negative voltage across the resistor. I'll start plugging in the equations in just a second. Then we're going to walk. We're going to hit the capacitor. We're going from the positive to the negative, so we're going to go downhill because it's positive to the negative, where positive is high, negative is low. Great. Then we're walking. Walk. We hit the battery. We're going from the negative to the positive, so we're going uphill. Now in this picture, well, it says epsilon on there, so it's going to be uphill plus V of battery equals 0. Why? Because I ended where I started. Now you just plug in the equations for it. What is the equation for the voltage of a resistor? Negative I times R. What is the equation for the voltage of a capacitor? Rearrange this equation. V equals Q over C. What's the voltage of a capacitor? Just rearrange it. Q over C. Then we hit the battery. What's the voltage of the battery? It's just V. And our right answer is, if you put A, you got to get V in terms of the other variables. You don't want V to show up there.
Is C just like the favorite letter? Like, why are all these always C?
I don't know. That's random. There is no rhyme or reason to this. That is also a good rule of thumb for you all. Random has far more streaks in it than you expect. Random has far more streaks to it than you expect. So you all will notice when you review test 1, that test 1 is all in order of the content I covered. Do I actually give you all your tests in the order that is covered? No. What I do is I take the problems and I just move them around randomly. There's no rhyme or reason other than just put them all up. When I'm choosing answers, I do try to make sure there's kind of sort of a distribution of A, B, C, D. Make sure that that at least some of the questions have an answer that's D, some of the questions have an answer that's A. But when they get mixed around, you can get a bunch in a row. It's random. I'm not like trying to avoid that or trying to make it happen. Yeah. When you're going across the resistor, you're going in the direction of current, downhill. Current flows downhill. When you go to the capacitor, you go from the positive terminal to the negative terminal, also downhill. No, when you go in the direction of current. So that goes back to the previous slides on that we talked about. When you go in the direction of current, that's downhill. When you go from positive to negative, that's downhill. Yeah, we know the current's going to the right. You can see it in the picture. Yep. All right. Derivation. I am not going to actually derive this. I'm just going to show the next step that's going to build our differential equation. And then the next slide goes to the whole derivation. But for the sake of time, I'm not going to do it. So if you're like, what's going on here? We're going to do one little substitution. Remember that I is defined as dq dt. And in fact, I'll make it a capital Q just for, it's fine. V minus, no, I'm going to make it lowercase q. And I'm going to make this one lowercase q as well, just makes things easier. dq dt times r minus q over c. Okay. This is a foreshadowing of things you're going to have to do in differential equations. A differential equation is something that looks like this. I have a derivative in it. And in this derivative is a variable that shows up somewhere else. I have this dq and I have a q. How do you solve this? Your end goal is to build an integral with q's on one side and a dq, and dt has everything else. How do you get rid of this dq, this dt? You integrate both sides. So this is a foreshadowing. In fact, on this side, it ends up being 1 over Q. I'll quickly kind of show it on the next slide. But there's some so great. dq dt minus Q over C. Then I multiply everything by C to get it out of the bottom. All I did was I took the C and I multiplied everything by it. Great. Then you get this form. Everything's got a C in it. Yay. Get the dq dt by itself. Then rearrange it. Take the CV minus Q. Bring it to the side with the Q. Take the dt. Move it to the other side. Q's are all together. Bunch of junks on the other side with a dt. What do you do now? Integrate it. Integrate your Q's. Integrate the dt. What's the integral of dq over cv minus q? It's a natural log. C is a constant. V is a constant. What's the integral of that? Natural log with all the junk. What's the integral of 1 over rc dt? T over rc. Do a bunch of rearranging, and you get the charging equation. The whole point of this is to build this equation. You actually already had a lab on this, I think. RC circuits. This is the charging equation for an RC circuit. Q equals Q max times 1 minus e to the negative t over RC. If you want the current, take the derivative of it. Remember, current is defined as dq dt. Just take the derivative with respect to time to get the current equation. Something that's important here. I'm going to rewrite this equation over here a different way. Q equals Q max, and Q is a function of time. It's charging. It does not happen instantaneously. The charge changes over time. 1 minus e to the negative t over tau. This little variable here is called the time constant. It is the Greek letter tau. This little symbol here is tau. It is a small little t without the top part. That is tau. This is something that's really commonly called the time constant. It's r times c. If I say find the time constant, you just multiply r times c. It's really straightforward. All right. That's the charging equation. What's the discharging equation? It's going to look very similar. It's derived the same way, but just a different circuit. There's just no 1 minus. There's no 1 minus. This is an exponential decay. This is, I don't quite know what to call this graph. Call it like a tabletop where it charges and then at some point it reaches some maximum charge and it stays there. Discharging is exponential decay. The charge decays downwards to 0. All right, so let's apply this really quickly. Yeah, I don't know if we'll be able to solve it in time, but we'll try. It's an easy problem. A 50 microfarad capacitor is connected through a 300 ohm resistor to a 12 volt battery. What's the magnitude of the final charge of the capacitor? I want Q max. What is Q max going to be? Let's derive it really quick from the equation. Q of t equals Q max times 1 minus e to the negative t over RC. So this might not necessarily reveal it. So actually, I'm just going to tell you the trick to get Q max. When is it Q max? When it has all the voltage. So how do you get Q max? C equals Q over V. When is it fully charged? When does it have the most charge? When it's fully charged. Then you just use this equation. C equals Q over V. So if you all want Q, take the voltage of the battery, take the capacitance, multiply them together. Done. Great. There's Q max. How long will it take to charge? So I'm going to show you all how to do that. How do we get how long it takes to charge to 1/2 Q max? So we're trying to figure out t to time. We're trying to solve for time. Here's the key. What is my charge when I'm at this point? At some time, I equal 1/2 Q max. How is that useful? Take this and put it in the equation. 1/2 Q max equals Q max times 1 minus e to the negative t over RC. What happens to my Q maxes? They cancel. You know R, you know C. You're solving for time. It's just an algebra problem. Not too bad. How long will it take for the charge to reach 0.9? Do the same thing, but make it 0.9 instead of 1/2. This is kind of like a half-life problem. In your chemistry classes, they said, how long does it take the population to reach 50% of the size? It's the same problem. All right, that's it, y'all. Next week, Meneg Field. It's going to be a grand time. You too?